Bismillah ar-Rahman ar-Rahim. Welcome everyone. I am Dr. Chaabani Walid. We will cover the fundamental concepts of Chapter 1 and the Strength of Material 1 course. Together we will understand how structure elements handle external force and how we ensure safety and structure stability. Today I will briefly introduce the first two chapters of our course on Strength of Materials 1. We will cover the fundamental of generalities on the strength of materials. Then we move to geometric characteristic of cross-section, to key areas in strength of material. By the end of this chapter, the student will be able to understand the fundamental hypothesis of the strength of the materials and elasticities, identify mechanics of materials is applied to guarantee three essential design criteria: strength, rigidity, and stability across various civil engineering projects like buildings and bridges. Continuity. The material is continuous, meaning it has no cracks or cavities. Homogeneity. At every point, the material has the same chemical properties. Isotropic. The physical properties are the same at every point and in all directions. Elasticity. All bodies are perfect elastic. Bernoulli hypothesis. A plane section remains a plane after deformation. Superposition. The total effect caused by the action of several forces is equal to the same of the effect to do the action of each force separately. We start with the principle of linear elasticity. This hypothesis assumes that deformations are fully reversible and directly proportional to the applied stress, governed by Hooke's law, sigma equal E multiplied by epsilon. From an engineering perspective, this means that as soon as external loads are removed, the structural member returns completely to its original informed shape without any permanent plastic deformation. Then we move to constitutive material behavior to structural kinematics. We apply Bernoulli hypothesis, also known as the assumption that a plane section remains plane. This kinematic rule detects that cross-section originally plane and perpendicular to the natural axis stay plane and perpendicular to it even after bending axes. In terms of engineering impact, this assumption directly simplifies a beam bending theory by establishing a directly linear distribution of axial strain across the depth of the cross-section. Finally, combining linear material behavior with a small deformation allows us to leverage the principle of superposition. This principle states that the total combined effect of multi-external load acting together is equal to the algebraic sum of the effect product by each load acting individually. Practically speaking, this gives us a powerful analytic advantage. Instead of the solving a complex multi-load scenario all at once, we can break down a complex load combination and simple components, analyze each individually, and simply sum the results. Cartesian and cylindrical coordinate system. We model structure elements along a longitudinal axis X and transversal axes Y and Z. Standard unities are strictly fluid expression stresses in megapascal. Structural solid classification in strength of material 1. Our primary focus is on 1D line element such as beams and bars, where the longitudinal dimension is significantly greater than the cross-sectional dimension. To understand how structure handle loads, engineers analyze their external connection, which enforce kinematic restriction by exerting reaction force that acted as any now in static calculation. In 2D planar system, these connections are categorized into three basic types according to the degree of freedom they restricted. The first, temporal support. This boundary condition prevents translation along a singular axis, typical perpendicular to the contact surface, leaving the remaining movement and rotation free. Because only one motion is restricted, it generates one anyhow reaction force. Second, double support. This type restricted to degree of freedom by preventing translate along both orthogonal axes, X and Z, will stay all in free rotation. Consequently, it's developed to anyhow reaction force. Last, triple support. Here 3 degrees of freedom are restricted, preventing horizontal translation, vertical translation, and rotational motion internally. This complete restricting process 3 anyhow reaction, 2 force competence, and 1 reactive moment. Static equilibrium and the principle of action and reaction, building directly a no boundary condition. Under this principle, a stricter point must maintain equilibrium. When not external force acts, it meaning the vector sum of all applied force and support reaction equals 0. Structural systems are categorized by their degree of static indeterminacy H, which measures the difference between anyhow reaction Q and equilibrium equation B, to reveal the number of resulting supports in a system. The first system, hypostatic systems, H less than 0. In this scenario, the number of anyhow support reactions, Q equal to, is strictly less than the 3 static equilibrium equation, P equal 3, because there is insufficient support to maintain equilibrium. In this system, cannot safely support external load. Second system, isostatic systems, H equals 0. Here the number of anyhow reactions, Q equal 3, exactly balance the number of equilibrium equations, P equal 3, only asked to solve for all internal action and external reaction using static law. Finally, system, hyperstatic system, H greater than 0. In this case, the number of anyhow reactions, Q greater than 4, excite the available equilibrium equation, P equal 3. To solve for this external anyhow reactions, static equilibrium equation alone are on longer sufficient, requiring us to incorporate material deformation and compatibility conditions. Structural resistance depends heavily on the section geometry. We evaluate the centroid G, moments of inertia A, and apply Huygens parallel axis theorem for the composite section. We start with a shift from static to deformability. Unlike general statics, which assigns completely rigid body to determine external reactions, strength of materials allows for material deformation to evaluate internal stresses, strain and structural behavior under applied loads. Then we move to stability. Students learn to classify structural systems as hypostatic, isostatic, or hyperstatics depending on their degree of freedom and boundary condition, laying the groundwork for solving both simple and complex structures. After that, we move to cross-section optimization, structural resistance to dependent shear, axial loads, and torsion depending heavily on the geometric properties of the cross-section, such as the center round, static moment, second moments of area, and radius of generation. Thank you for your attention. I am